In the previous video, we found the derivative of this equation, 3 root x plus 5 on x squared root x minus 4 on x. I didn't go the step further that I needed to, which was to calculate the slope when x equals 2. To be honest, this isn't the sort of question that you would generally ask to be calculating with a substitution for x, but I will go through and show you how it works. Really what we need to think about is what does this x to the minus a half and the x to minus 7 halves, what do these two things actually mean? Remember that x to the half is the square root of x, and so x to the minus half is 1 on the square root. X to the 7 halves, or x to the, oops, wrong pen, x to the minus 7 halves is 1 on x to the 7 halves. And 1 on x to the 7 halves is 1 on the square root of x to the power of 7. And if you're not sure about that, you need to go and review your index laws. But basically, if we rewrite the equation with using roots instead of indices like that, it's going to look like this. Oh, sorry, we've done the substitution here, I beg your pardon. And in fact, that x should be a 2. And once you've done that, you can just put this straight into your calculator. It's not the sort of thing that you would be asked to calculate manually, but this is what it's going to look like. So here we've expressed it with roots instead of indices and positively expressed roots. Honestly, you can work it out if you want. That's totally up to you, but it comes to 32 minus root 2 on 32. Not something you would be asked to calculate without a calculator, for sure. All right, last example, example 5.2. A big thing in calculus, one of the big ideas in calculus is the motion of objects. In maths, we don't tend to talk about objects in real life. We talk about single particles, and we talk about the mathematical movement of the particle rather than the genuinely physical movement in three-dimensional space that you would investigate in science, more specifically physics. Our very first movement question, and it's called kinematics, which is the mathematics of movement, is this one here. So an object moves in a straight line with position from O being the origin, given by s of t equals t squared minus 4t plus 3. All the way back up here on the previous page, we talked about this, and all of my highlighting has moved. We've talked about f of x is, we find the derivative f dash of x by differentiating with respect to x. So whatever is inside the bracket, that's what we're deriving with respect to. So now down here, we're dealing not with f of x, but s of t. So to find the derivative of that, we're finding ds dt, so the change in s with respect to time, and it is effectively the equivalent of dy dx. So ds dt, we do it exactly the same way, except this time t is the variable that we're deriving. So looking at our function, the 2 comes down as a factor. T, 2 minus 1 is 1, so t squared derives to 2t. Minus 4t derives simply to minus 4. So ds dt is 2t minus 4. And then the question says interpret its meaning in the context of this question. So ds dt is the change in speed. Sorry, I beg your pardon. It's the change in displacement. S is displacement. And t is time. So it's a change in an object's position with respect to time. The faster it changes position in a certain period of time, the further it changes position in a certain period of time, the faster the object must be moving. So this ds dt is simply the equation which shows us the object's velocity, so the change in displacement with time. It is velocity, not speed, and we'll talk in a subsequent chapter about why it's velocity and not speed. But basically, it's the object's change in displacement with respect to time. WRT stands for with respect to time, which is also known as its velocity. Okay, find the value of ds dt when t equals 3. So when t equals 3, ds dt equals 2 times 3 is 6, minus 4 is 2, and interpret your answer. So that means when t is 3, and I don't think we've got any information about time, so presumably time is seconds or minutes. When t is 3, the object's displacement is changing at a rate of 2 centimeters per unit of time. Not sure what that time is, so it could be centimeters per second, centimeters per minute, depending exactly what it is. But that's the interpretation in that context. And that's it. That's enough to get you going now on exercise 15. And I hope that you will enjoy using the shortcut rules and that they will be nice to use after you've spent so long doing first principles derivatives. All right, see you in class.